Hey y'all, welcome back. Tonight's homework is all about finding limits algebraically, and I'm going to be honest with y'all, I love doing algebra. I think it's fun. It feels like solving a puzzle, just activates some kind of part of my brain that feels good. But I know that that's not going to be the same for everyone. In fact, most most students are going to struggle with the algebra. So hopefully we can do a good job of going through these problems and really identifying kind of what I'm looking for as far as how to solve them, because they're not all going to be solved the same way. We went over a few different techniques in class, and part of the challenge as you go through these limits is identifying what technique to use. So as we go through these, I'll try to explain what I'm seeing and how I know kind of which direction to take. So number one, it says clearly describe why direct substitution may not be used to determine the limit as x approaches 2. So we can see that if we were to plug in 2 or substitute 2, if we were to try to find f of 2 here by just simply substituting it in, there we go. By just substituting in, okay, let's try this again. One last time. If we just try to substitute f of 2 in, we're going to get 2 squared minus 5 times 2 plus 6 over 2 minus 2. Now we have a little bit of a problem here because that denominator, up top we get 4 minus 10 plus 6. I don't really care what that is. In the denominator though, I get 0, right? This is undefined. And so when a rational function is undefined, when you have an x value that makes the denominator 0, one of two things can happen. Either you've got a vertical asymptote there, so you have a non-removable discontinuity, or you have a hole or a removable discontinuity. Now, just by looking at it immediately, it may not be clear which one it is, but here's kind of what you want to be looking for. If the value that you plug in makes the denominator 0, it's going to be undefined. But if that same value also makes the numerator 0, so notice 4 plus 6 is 10 minus 10 is 0, then that usually indicates that we're going to have a removable discontinuity or a hole. And so to identify where that hole is, we would factor the numerator and cancel out the like factors. So I'm going to rewrite this as f of x equals x minus 3 times x minus 2, which is what I would get if I factor that numerator, over x minus 2. Now, I'm not going to spend really any time talking about factoring. I've got a few videos on how to factor. You could go back to some of my Algebra 1 videos on how to do that. At this point, you should be pretty good with factoring. Most of the factoring problems you're going to have are going to kind of fall into the easy category where the leading coefficient or the a value is 1. And so you should just be able to find two numbers that multiply to give you the constant and add or sum to give you the linear coefficient. So that would be -3 and -2. So let's go back and actually answer this question. I just wanted to give you a little bit of information here so you can kind of see what's really happening. It says, why can direct substitution not be used here? Well, if you use direct substitution, if you substitute 2 into the function, f of x is undefined. So that's really the underlying issue here. You can't figure out what the limit is by just simply plugging in 2. Now, does this mean the limit does not exist? It could mean that. If that value is only making the denominator 0, then you're going to have a vertical asymptote or a non-removable discontinuity. But if that also makes the numerator 0, then what you have instead is a removable discontinuity, in which case the limit would exist. Okay, the limit does exist because there is a hole at x equals 2. Okay, we haven't talked about continuity yet, but if you want to be a little fancier about how you word this, a whole another way of saying that is removable discontinuity. Okay, so anyway, this problem is really just I want you to kind of be thinking in terms of, when do limits exist, when do they not exist, and what conditions need to be met in order for them to exist. If we were to try to find that limit, which this is not actually asking us to do, we'll do some ones like this later, you would factor it out like I showed you, cancel the common factor, and then use direct substitution. Let's take a look at number 2. They're giving us a piecewise function. It says f of x is equal to the square root of x minus 4 when x is greater than 4. Okay, so this is like to the right of 4. And then it is this linear function 8 minus 2x if x is less than 4. So this is to the left of 4. And maybe I'll be a little bit more specific here. When I say 4, I'm talking about x equals 4. So let's try to sketch this graph out. Okay, let's start with the easier portion, the linear function. When I'm trying to sketch out a piecewise function, I sort of ignore the fact that it's piecewise when I first approach it and just try to graph the line or the curve in its entirety to begin with. So 8 minus 2x has got a y-intercept of 8. Can't really, 1, 2, 3, 4, 5, 6, 7, 8. Not going to be able to fit that, but the slope is negative 2. So I'm going to go down 2 over 1. Can't really fit that point. That's okay. Down 2 over 1, down 2 over 1, down 2 over 1, and so on. So this would be the line if that's all it was. It's a linear function, right? But this is saying that that is only going to be valid for when x is less than 4. So I'm going to go back and erase anything that is greater than 4. So 4, just to be clear here, x equals 4, 1, 2, 3, 4 is right here. So this is going to be kind of our cutoff point. And I'm going to erase everything that is to the left of x equals 4. And in fact, I don't know how that just moved over like that. Can I undo that? It's weird. Never seen that happen before. The other thing I'm going to do is I'm going to change this closed dot to be an open dot because it does say strictly greater than 4. Okay, so now I'll look at the square root graph. That's the square root of x minus 4. So that's the parent square root function, but shifted to the right 4 units. Oh, wait a minute. Oh, goodness. Oh, goodness. I'm backwards here. Oh, let's back it up a second. Well, let me redraw that. There we go. Okay, let's back that up. We want to keep this line to the left of 4. So actually, I want to erase everything to the right of 4. My bad, y'all. Some of you are going to just like kind of pause the video there and be like, no, Mr. Schuler, what are you doing? Okay, so there we go. That looks much nicer. Okay, so now let's go back to that square root function, which is the parent square root function, but shifted to the right 4 units. So let me just kind of show you what the parent square root function looks like. The square root of 0 is 0. The square root of 1 is 2. The square root of 4, wait, what did I just say? The square root of 1 is 1. The square root of 4 is 2. And so the graph does something like this. Okay, what it really is kind of half of a sideways parabola. Now, this is the parent function. This is just y equals square root of x. But this is x minus 4. So that's going to shift this to the right 4 units. So let's get rid of all this and kind of start over here at 1, 2, 3, 4. We've got an open circle because it's not equal to. And then we can't really fit much on here, but the graph is basically going to go something like this. Okay. Now that we have a better picture of what's happening, we can start to answer some of these questions. So I'm going to go a little bit out of order here. So we have the graph, but you can see that like f of 6 and f of 0 are kind of off the grid here. And so what might be easier is if we just use the equation instead of the graph. So f of 6, we're going to evaluate that by substituting 6 into x. Now, since 6 is greater than 4, we are going to use the top function. Okay, 6 is greater than 4, so f of 6 should be the square root of 6 minus 4, which is the square root of 2, which is about like 1 point something or other. And so if I go out to 6, which is out here, you can see that this is like slightly above 1. So that makes sense. F of 0, now 0 is less than 4, so I'm going to use this one. So 8 minus 2 times 0, the 8 minus 0, which is just 8. And we knew the y-intercept here was 8 anyway, so you probably didn't even need to do the algebra here. But yeah, so that, yeah, f of 0 is 8. F of 4. Now, we have two pieces, one of which that is defined for x being less than 4, and one of which is defined for when x is greater than 4. Neither one of these is defined for when x is 4. Yeah, so none of them are defined for when x is 4. I'm going to clean this up a little bit. It's a little easier to read. Oops. So it's just undefined. Yeah. The next couple of questions are referring to limits. So D says the limit as x approaches 5. So if I look at the graph and I try to see, like, when is the graph, I'll get rid of this real quick. When is the graph approach, or what is the value of the function approaching when x approaches 5? And we need to examine both what's happening on the left side and the right side of 5. So 5 is this point right, a little bit, it's kind of close there, right there. And so as I approach it from the left, it's getting closer to 1. As I approach it from the right, it's also getting closer to 1. So this would just be 1. And I'll try to stay consistent with the coloring here. It's on the red piece. Okay, there's no work to show, so I guess I'm just going to leave it like that. The boxes are kind of getting in the way here. Let's clean that up a little bit. All right, E, the limit as x approaches -2. Now, -2 is less than 4, and that is off the grid here. That's okay, but we should know that this graph is continuing. So when x is -2, that's going to be some point up here. So it's going to be bigger than 8. And you might be able to just figure it out, but I think it might be easier to just plug it into the equation. So 8 minus 2 times -2 is 8 plus 4, which is 12. And that's bigger than 8, so that looks like that could be right. So it seems like a reasonable answer. For F, it says the limit as x approaches 4. So since x is approaching 4, we have to check from the left and the right. Now 4 is kind of that break point. It's that point where the left-hand side is meeting the right-hand side. So let me clear up this little highlighting here. And we can say, okay, well, as we approach 4 from the left and we approach 4 from the right, even though the function's undefined at 4, the limit as x approaches 4 is 0. Just do it in both colors because it's you're kind of looking at both sides there. Number 3. Okay, so all this other stuff is mostly review. I guess not totally, but this is really what we focused on today. Determining these limits algebraically. This is where the fun begins. So 3a, we want the limit as x approaches 3. Now your go-to strategy should just be to go ahead and plug it in. Okay, plug in the value, see what happens. If we have an output, then we're good to go. If we get something that's undefined, some indeterminate form, then we'll have to go back and use one of the strategies we talked about. So 3a, I'm just going to start by trying to plug in 3. Let's see if that works. Square root of 3 plus 1. over 3 minus 4. That's going to give me root 4 over negative 1, which is negative 2. And there you go. There's our limit. Okay, B. I've got two quadratics here. Whenever I see those quadratics, and this is at the very beginning of this video, I said I would talk about like what I see in the problems that kind of indicates or gives me at least a hint of what I should be doing. Anytime I see these quadratics, my brain is immediately going to factoring. Like I will probably have to factor this. And if you were to try to just use direct substitution here and plug in the negative 1, you're going to get 1 plus, actually, can we plug that in? Does this work? No, it doesn't actually. I got excited there for a second. 1 plus 3 minus 4, 4 minus 4 is 0. So unfortunately, direct substitution is not going to work. So we're going to have to say that this equals the limit as x approaches negative 1. Don't forget about that limit. You got to write that. Now, once you start plugging in numbers, you can get rid of it because that's when you're actually evaluating the limit. But until that happens, you have to write the limit. And I'll factor the numerator. Two numbers that multiply to give me 5 and add up to 6 are going to be 5 and 1. So those are my two factors, x plus 5 and x plus 1. And two numbers that multiply to give me negative 4 but add up to negative 3 would be negative 4 and positive 1. So x minus 4 and x plus 1. Now, typically, you're not allowed to just go ahead and cancel out those terms. They are two different functions, but their limits will be the same. And really, the only difference between them, we talked about this in class, is that you have the whole, all right? Like this function is going to have a whole at x equals negative 1. If you remove the whole by canceling these out, you do have a different function, but it's only different by that 1 point. So the nice thing about the limits is algebraically, you are allowed to cancel those out. Okay, so we will, and when I say cancel out, what I really mean is we're going to reduce these factors to 1. Right? Anything divided by itself should be 1, as long as it's not 0, right? So let's go ahead and finish this off. Limit as x approaches negative 1 of x plus 5 over x minus 4. Now we can go ahead and plug in that or use direct substitution with that negative 1. So we get negative 1 plus 5 over negative 1 minus 4. And what is this? Looks like 4 over 5. The 5 is negative, so we'll say negative 4/5. Letter C. We got a bunch of fractions, which, will scare most people. But you know what? Fractions aren't so bad once you get the hang of them. Let's go ahead and just do it. So to combine these fractions, when you see these fractions, you're going to want to try to simplify this as much as possible. So like you want to add those fractions by finding a common denominator so that we can write this numerator as just like one big fraction divided by the 4 plus x. And then that way we can rewrite this as just a single fraction. And usually when you do that, you can find something to cancel or reduce to 1. And then you can go ahead and plug in the negative 4. But hopefully you see why we can't plug in negative 4 right away. Because 4 minus 4 is 0. I can't divide by 0. So to find this common denominator, I'm going to multiply this top fraction by 4 over 4 and the 1/4 by x over x. Trying to stay consistent with my notation here. So this will equal the limit as x approaches negative 4 of 1x over 4x plus 4 over 4x over 4 plus x. Now I can combine those two fractions in the numerator, so they have a common denominator, x plus 4 over 4x divided by 4 plus x. Now anytime you're dividing a fraction, it's equivalent to multiplying by the reciprocal. So this would be the limit as x approaches negative 4 of x plus 4 divided by 4x. And instead of saying divided by 4 plus x, I'm going to say times 1 over 4 plus x. So I'm not going to write this as a separate step and just go straight to this and erase the 1. So now we can see that we can reduce the x plus 4 over x plus 4 reduces to 1. So this is going to equal the limit as x approaches negative 4 of 1 over 4x. Now we can go ahead and use direct substitution, plug in that negative 4, and we get 1 over negative 16. The fraction problems definitely take the most work. Yeah. D. Now, in this problem, I see that I've got a square root in there. And so anytime I've got a denominator or even a numerator where you've got a square root plus or minus a constant, that's going to be one of these rationalizing problems where we have to multiply both the numerator and the denominator by the conjugate of the denominator, or the conjugate of, actually it could be the numerator, so the conjugate of whichever side has that square root. In this case, yeah, the denominator. So I'm going to multiply both of these, the numerator and the denominator, by root x plus 3. Now, on the numerator side, I'm just going to leave it alone. I'm not going to multiply that out because I am going to be looking for something to cancel. And since this is already in factored form, I'm just going to leave it that way. And then when I didn't multiply the denominators, the whole reason why you multiply by the conjugate is so that you can get rid of the square root, essentially. You're not going to have a square root in the denominator anymore, because if I multiply root x by root x, I just get x. If I multiply root x by 3, I get 3 root x. But because we're doing it with this conjugate multiplication, you're also going to get a minus 3 root x, and those two will just add up to 0. And that's going to happen every single time when you do it this way. And then the last term will be 3 times negative 3, which is negative 9. So you should expect something like this to happen where you can get that denominator to reduce out and cancel out with a factor in the numerator. Now, hopefully you see why I didn't want to multiply these numerators out. And I would always kind of hesitate to do that anyway. All right, so this is going to be the limit as x approaches 9 of square root of x plus 3. And at this point, we can just use direct substitution. So the square root of 9 plus 3 is just going to be 3 plus 3, which is 6. All right, we've only got a couple left here. E says the limit as x approaches pi over 2. Let me get rid of that box here. Of sine x. So the sine function is a continuous function, and we still have not quite gotten to continuity yet, but we sure have alluded to it quite a bit up to this point. But when you have a continuous function like sine x, you can just go ahead and use direct substitution. There's really no tricks here. So the sine of pi over 2 is going to be 1. Now, you should just know that, quite honestly, but just to give you like a little bit of background, little refresher on the unit circle. Pi over 2 is going to be equivalent to 90 degrees. And when you're trying to evaluate sine, what you're really trying to find here is the y coordinate on the circumference of the unit circle for that angle. So here's the 90 degrees of the pi over 2. We want to find the y coordinate of this point. This point is 0, 1. So that's why we're grabbing the 1. If it were cosine, we would grab the 0. So cosine of the angle is equal to the x coordinate. Sine of the angle is equal to the y coordinate. There's a lot more to it there. You might want to go back and review your pre-calculus trigonometry stuff about the unit circle if you really have no recollection of what I'm talking about here. Okay, one last one here. We want the x to go to 0, and we see that obviously that's going to make the denominator 0, so we can't use direct substitution. But what we can do is factor out an x as though it is a GCF, and actually it is a GCF on the top. So just leave that negative 2x plus 1 there, the x on the bottom. Now I can reduce the x's then we're going to be in business here. So we got negative 2x plus 1. Now we can use substitution. So we're going to substitute the 0 into x, and we get negative 2 times 0 plus 1, which is just 1. And yeah, that's it for this page. Let's move on. Letter G. Okay, can't plug in 1. Most of these are not going to be able to just use direct substitution right away, unfortunately. Those are kind of the easiest problems because you're just plugging it in and simplifying the expression, but that is not going to be too frequent. Okay, so here we want to factor out an x from the numerator. We get the limit as x approaches 1 of x times x squared minus 1 over x minus 1. And you might say, well, wait a minute. Nothing's canceling out yet. And that's because we could do a little bit more factoring. We can factor out that x squared minus 1. It is a difference of two squares, so we can write it as x plus 1 times x minus 1 over x minus 1. And now we can get those x minus 1s to reduce. So this should equal, let's move this up a little bit, the limit as x approaches 1 of x times x plus 1. And now we can go ahead and just plug in 1. So 1 times 1 plus 1 is 1 times 2, which is 2. H, we've got the limit as x approaches negative 1. Can't use direct substitution here, but you can factor. Now I did say that most of them are going to be like the easy factoring ones where, you know, the leading coefficient's 1, but every once in a while you'll see one that isn't. But if it's set up like this, you should have at least a suspicion that one of the factors is going to be x plus 1. And 9 times out of 10, that is going to be how it's set up. There may be an oddball problem where that doesn't happen, but in that case, you wouldn't have a limit anyway. You would just have, you know, a vertical asymptote. So we'll try at least to factor this out. Let me make sure I write limit here. The limit as x approaches negative 1 of, I'm going to just like assume one of the factors is x plus 1 so I can get these to cancel and let that inform me on what the next factor is going to be. So if the first term has to multiply to 2x, that means this has got to be 2x. 2x times x is x squared. And then if this does work out, 1 times this number has got to be negative 3. So that means this has got to be negative 3. Now, just to like double check and make sure this is true, I can multiply my linear and constant terms, my inner and outer terms, and make sure they do add up to negative x. We got 2x minus 3x does add up to negative 1x. So that checks out. At this point, we can reduce these factors to 1. And so we get the limit as x approaches negative 1 of 2x minus 3. Now we can use direct substitution. 2 times negative 1 minus 3 is going to be negative 2 minus 3 is negative 5. Letter I. We want the limit as h goes to 0. And unfortunately, direct substitution, not going to work. But I do see that square root in there. So that's my indication I'm going to have to use the old conjugates. So I'm going to multiply this thing by the square root of 1 plus h plus 1 over the square root of 1 plus h plus 1. So I'm going to go ahead and multiply that out. We get the limit as h approaches 0. The denominator I'm going to leave in factored form. And then the numerator is going to become 1 plus h, and then 1 times 1 is just 1, so minus 1. So this will equal the limit as h approaches 0 of the 1 minus 1 is just 0. So h over h times the square root of 1 plus h plus 1. I can get those h's to reduce to 1. So we have the limit as h approaches 0 of 1 over the square root of 1 plus h plus 1. And now if I plug in 0, I'm going to be safe. So this is just going to be 1 over the square root of 1 plus 0 plus 1. Almost running out of room here, but I think we're going to get there. 1 plus 0 is just 1, so we have 1 over 2. Whew. All right, J. Now, J, we're going to try to plug in 1. Doesn't work, of course. We get this indeterminate form, 0 over 0. But what we can do is factor both the numerator and the denominator. The denominator is a difference of 2 squares. So you should know that when you factor a difference of 2 squares, it's just going to be the first term plus the square root of the first term plus the square root of the second term. So in this case, x plus 1 times the square root of the first term minus the square root of the second term. Now for the numerator, that is a difference of cubes. Okay, and that's going to factor to be x minus 1 times x squared plus 1x, or just x, plus 1. Now, I'm just going to put a little star here. This is called a difference of cubes. If you're not familiar with that factoring trick, go ahead and do yourself a favor, Google that. There's tons of YouTube videos out there to explain it. But you might want to just commit that to memory, how to factor either a difference or even a sum of 2 cubes. We're not going to go over that right now. So limit as x approaches 1, we see that these x minus 1s are going to reduce to 1, leaving me with x squared plus x plus 1 over x plus 1, and now we can substitute in 1. So using direct substitution, we get 1 squared is 1, plus 1 over 1 plus 1, which is 3 halves. All right, we're on our last page here. Letter K. All right, this list of letters is pretty long here. It said 10 problems, but I feel like it's closer to 20. Okay, so this one will be pretty similar to the last one. We can't plug in 2, but we can factor that denominator as a difference of 2 squares. So this is going to be the limit as x approaches 2 of 2 minus x over x plus 2 times x minus 2. Now, you might be thinking, well, hang on a second. Like, we don't actually have anything that can cancel here, right? We don't have the same factor on the numerator and the denominator, although we do have 2 factors that look very similar. We've got the 2 minus x, but on the denominator is x minus 2. So what we can do is force that numerator to be the same factor as the one in the denominator by factoring out a GCF of -1. So if I factor out a -1 out of this numerator, this is going to become -2 plus x, which is x minus 2. If I distribute this -1 back in, I'm going to get the 2 minus x. This is going to come up from time to time, so don't get freaked out if you've got 2 factors that are sort of backwards. You can fix that by factoring out a -1. So now I can get those two binomials to reduce to 1. So this is going to equal the limit as x approaches 2 of -1 over x plus 2. And now I can go ahead and just plug in 2. So I'm going to get -1 over 2 plus 2 is 4. Letter L. Another factoring problem. I'm just going to assume that we've got to factor it. I guess I could go through the arithmetic real quick. 2 squared is 4. I'm just checking this. Well, actually, hang on a second. I thought that this maybe was going to just be another factoring and canceling, but 2 squared is 4. 6 times 2 is 12. 4 and 12. Let's just go ahead. I think we can use direct substitution right away. Let's go for it. 2 times 2 squared plus 1 over 2 squared plus 6 times 2 minus 4. Yeah, we're going to have some success here. 2 squared is 4. 4 times 2 is 8. 8 plus 1 is going to be 9, but I'll just do it kind of slower here. 4 plus 12 minus 4. So this is going to turn out to be 9/12. Or if you reduce it, which you don't have to do. In fact, really, if this were a free response question, you could technically be done here. Now, if it were a multiple choice question, they are going to be simplified and reduced, so it's good practice to know how to do that. But if this were a free response question, I wouldn't even go past this step. But if it were multiple choice, I would want you to know that this is going to reduce. If we divide both the top and the bottom by 3, we're going to get 3/4. And our last question of the homework, is there such a number that this limit exists? If so, find the value of a and the value of the limit. Now, this is a pretty challenging question, I think. This definitely should, this is a thinker, if you will. So it says, if so, find the value of a and the value of the limit. So if there is a number so that this limit exists, now let's see, the denominator here, let's go ahead and factor this. I'm going to rewrite this as the limit as x approaches -3 of 8x squared plus 8ax plus a plus 10. Go ahead and factor that denominator as x plus 3 times x minus 2. So we can see -3 is going to cause the denominator to be 0. But in order for there to, so like if the limit does not exist, then that number -3 is not going to make the numerator equal 0. But if we want the limit to exist, we want there to be a whole or a removable asymptote at -3. Then the numerator has to be divisible by x plus 3. Or in other words, the value of this function, this numerator, when x is -3, must be 0. Let me say that again, but write it. I'll completely write it out here. So if the limit exists, then not only does -3 make the denominator 0, but x equals -3 must make the numerator equal 0, right? So what we can do is take this x minus 3, substitute it in for x, and then solve for a. Let's go ahead and do that. So 8 times -3 squared plus a times -3 plus another -3. Let me back this up. See if I can just move it over so I don't have to rewrite it. Nope, I'm just going to rewrite it. That's okay. So let's try that again. 8 times -3 squared plus a times -3 plus -3 plus 10 equals 0. Let's simplify this a bit. -3 squared is 9. 9 times 8 is 72. So we have 72 minus 3a minus 3 plus 10. I'll just go ahead and clean that up. 10 minus 3 is 7. So 72 and 7 is going to be 79. Subtracting 79 from both sides gives me -3a equals -79. And then dividing by 3. Now, I'm going to do a little workout to the side here. It's a negative divided by negative, so I know the result's going to be positive. So 3 goes into 7 twice. Looking at these answer choices and not feeling very confident that my arithmetic is going to pan out here. So let's see. So no, this is not gonna be a rational function. Let me take a quick look and see what I did here. Oh, you know what? I plugged in -3 here. That should not have gone there. That is an A. Well, you guys see, I like to do these problems live. I could go back and edit that out, but I kind of like you to see the mistakes I make and just know that, hey, even Mr. Schuler, as he's working out through the algebra, even though he loves doing the algebra, man, sometimes you make a little error somewhere. So let's go back, and hopefully we don't have to change too much here. So I'm gonna have to go back, and I'm just gonna erase, I guess, up until this point right here, right? Because all that should be good. But then we do have this extra a plus 10, right? So now, hopefully this will work out a little better. 72 and 10 is going to be 82. Negative 3a plus a is going to be minus 2a. Still not liking that negative. Let's just see. Oh, no, it's going to be okay. It's going to be okay. Yeah, when it starts getting late at night, Mr. Schuler has a tough time focusing here. Okay, yeah, we're going to subtract 82 on both sides, and then divide both sides by negative 2, and we get 41. Okay, there we go. It's a good thing this one's a multiple choice, because then it can kind of guide and say, hey, wait a minute. If I'm like halfway through and I can see that I'm not getting any of those answer choices, then odds are I made an error somewhere, which in case I did. Okay, well, we got a is 41. So we can go ahead and eliminate a and d here. But now that we know a is 41, now we can start to evaluate the limit. So let's go back and forget all this and rewrite the limit. I'll use a different color so it doesn't get too cluttered here. But with that 41 kind of plugged into a. So 8x squared plus 41x plus 41 and 10 is going to be 51. Oh, God, that's going to be like really terrible factors. But it's okay because the denominator is going to be like pretty easy to factor. And so my assumption is that we're going to have an x plus 3 in the numerator somewhere. So let's go ahead and factor the denominator as x plus 3 times x minus 2. And so since I know that x plus 3 is what's going to have to cancel out, I'm going to just sort of guess, hopefully an educated guess here, that x plus 3 is going to be one of the factors and work towards getting the other factor to multiply to give me that 8x squared behemoth. So the first term would have to be 8x because 8x times x is 8x squared. And then 51 divided by 3. Let's see. So 3 goes into 5 once. I'm trying to do this no calculator here. And so 21 would be 7. So yeah, so 51 divided by 3 is going to be 17. And hopefully this works. 8x times 17 is 17x. 3 times 8 is 24. So 24 and 17 do add up to 841. So yeah, there we go. Those are our factors. So hopefully you're seeing that, if you know what one of the factors is, even if you've got a tough factoring problem, it makes it a little bit easier if you already know what one of the two factors is going to have to be. Okay, now we can reduce these two factors to 1. This is a brutal problem. I love it. These are the kind of problems that really get Mr. Schuler going here. Okay, the limit as x approaches negative 3 of 8x plus 17 over x minus 2, and now we can substitute in that negative 3. So this is going to equal 8 times negative 3 plus 17 over negative 3 minus 2 is negative 24 plus 17 over negative 5. Oof, all these negatives. Good Lord. All right. So, well, what's 24 minus 17? Would be 4, and 3 is 7. Yeah, so this is going to be negative 7 over negative 5, which is 7 over 5 is going to be 1.4. Boom. We got it. All right, what a problem to end this one off of, yeah? The algebra is pretty intense. It's getting to the point where you really got to be on your best game to get this algebra right. But hopefully you found this video helpful. That's it for tonight, y'all. Y'all have a great day.